In this video, we're going to take a look at an example of percent increase or percent decrease over a certain number of time periods. So this is called exponential growth, and it's different from linear growth because linear growth will take the same amount of increase or decrease for each time period, and exponential growth is going to have the same percent increase or decrease over certain time periods. So we're going to explore that a little bit with this example. Suppose that every year only 10% of the fish in a lake have surviving offspring. If there were 100 fish in the lake last year, there would now be 110 fish. If there were 1,000 fish in the lake last year, there would now be 1,100 fish. Absent any inhibiting factors, populations of people and animals tend to grow by a percent of the existing population each year. So in this example, the population of fish is growing by 10% per year. So let's go ahead and look at an example here. Let's say I start with 1,000 fish. All right, we'll start with 1,000. Now, if I want to find the number of fish next year, I have the 1,000 that I started with, and then I'm going to take 10% of 1,000 to get the number of fish next year. So I have the 1,000 I started with, and 10% of 1,000 is 100. So now I have 1,100 fish. So in general, what did we do here? All right, we took 1,000 fish, which was our population sub-zero, our initial population, and then we took 10% of that population. All right, so the initial population is like 100% of your initial population that you started with, plus 10%, that's the growth part. And so what we really end up with is 110% of our initial population. So population in year one is 1.1 times the population from the year before. All right, so this is called a growth multiplier or a growth rate. So in general, if you're growing by p%, a certain percent, then your multiplier is 100% plus p%. Okay, if you're decaying, if you're losing p% per year, then your multiplier is going to be 100% minus that percent. So let's say you were losing 10%. Well, that means you would only have 90% of the population remaining next year. So your multiplier would be 0.9. All right, so in this case, we gain 10%. So this is our multiplier, 110%, or 1.1. All right, so let's say we want to find the population in year two. All right, well, the population in year two is going to be 110%, or 1.1 times the population in year one. So 1.1, and I'm just dropping the 0 because we don't need it. It means the same thing. If you want to write the 0 there, you can. Times the population from year one, which was 1,100. And that comes out to be 1,210 fish. Okay, so now I have 1,210 fish in year two. Year three is going to be 110% of whatever year two was. So 110% times 1,000, multiplying it, 1,210, which is 1,331. All right, so you finish year 4 and year 5, and then we'll actually just do year 4. All right, pause the video and do year 4, and then think about what a general formula for that would be. So you should have gotten 1,464 rounded for the population in year 4. All right, so what's the pattern here? Well, if we look at these subscripts, let's get a highlighter here. These subscripts, in year 1, I multiplied by 1.1 times year 0. In year 2, 1.1 times year 1. Year 3, etc. Okay, so what if I want to find the population in year n, like a general recursive formula? I'm multiplying something by something else. Okay, so this is going to be p sub what? All right, what's going to go here? Let's just leave that for a second. This 1.1, remember that's your multiplier. So how did we get that? We got that by doing 100% plus the percent increase. Okay, so that's what's going to go here because we're doing a percent increase. We have 100% plus whatever percent increase. Maybe I should use a different letter than P since capital P is the population. I'm using little p for percent and capital P for population. Are we okay with that? Hopefully you're okay with that. All right, so since we're taking p sub n times, it equals our multiplier times the population from the previous year, that would be p sub n minus 1 for our previous year. All right, so this is called our recursive formula. 100% plus little p for percent, capital P for population. Now, as we saw with linear, recursive formula is great if you're just like generating a few values. But if I ask the question, what's the population going to be 50 years from now? What's the predicted population? I really don't want to run through this computation 50 times. So in order to help us with that, we need a explicit formula for finding exponential growth, and we will work on that in the next example.